talk a little bit about modeling and forecasting trends. So in this video, once again, we're picking up Module 3, moving a little bit further in the direction of predictive analytics and talking about how we might predict what's going to happen in a data set that has a time dimension. This is pretty typical for business data. There's usually a time dimension because the real world does have a time dimension. And we've already seen that a variable for something like a counter across time, 1, 2, 3, 4, 5, just going through the observations in the data set, can be very useful in predicting the next observation or predicting the observations in the data set if the data are evolving in a certain way, either increasing or decreasing as time goes by, which again is very common. Now, I used to teach an undergraduate forecasting class. We don't get to do very much of that sort of content in a class like this, but we do have an upper level DA elective for MBA students here in the College of Business for those of you who want to go a little bit further with the sorts of things that we're doing here in Module 3. At any rate, let's jump in. So, this is the idea. Data that has a time dimension often exhibits some sort of a regular pattern over time, which we would attribute to whatever sort of underlying components might be causing that. It's typically either something like a trend or something like seasonality. And I've already got some data open, so can't help but jump right over here and point to the month variable that I have over here in this orders data, which we've all seen a few times already. The month variable is just a counter, and I can use this month variable to predict orders. I could also potentially consider using transformed versions of the month variable, like month squared, month cubed, and some other things. And when I look at this data, I actually can perceive that there's some sort of a seasonal component to it. It looks like every 12 months, I have this peak that reappears, and so seasonality is going to be one of our next topics. But we're going to start here with deterministic trends, where we simply use a variable like month to predict what's happening. And I want to emphasize again that this is different from what you would do in a cross-sectional data series that has many different individuals. Say you're surveying people, and you can catch as many people as you can and try to get them to answer your survey, but whoever answers the survey first is going to be ordered first, and that number, person number 1, typically doesn't mean much. It might just mean that they responded to the email faster. So we treat that as random. But when this is the time dimension, it's actually something very meaningful, and we won't treat it as random. We will treat it as a real variable that we can use to predict what is happening. Okay. So a trend is a type of persistent long-term evolution in time series. There are different ways of modeling trends. We have things as simple as linear trends and as complex as, well, the sky's the limit. Here's an example. Now, GDP is the sum total, gross domestic product, is the sum total of all final goods and services produced and sold on an organized market during a specified period of time. We typically measure GDP for a country, the entire market in that country, and usually it's something like annual data, so a year worth of production of goods and services, everything that that country is able to produce in a year. This is already in logarithms because GDP tends to increase sort of exponentially, right? So we've transformed the data so that instead of increasing exponentially with time and growing at an increasing rate, it looks a little bit more linear. You can see that, yeah, sure, it does look like something I would predict, perhaps, with a line using the time dimension down here as my x values. And I know I've said this in a previous video, but using 1950, 1960, 1970, 1980 would fit a similar line to this data and give the same predictions as if I relabeled these axes as 1, 2, 3, 4, 5, 6, 7. I could rescale the x variable, but as long as I treat the picture the same, the line that will fit to it is the same, and the predictions are going to be the same. So the units down here in a time series don't really matter as far as predicting the outcome. But immediately I look at this and I say, is it really linear? I see that it has this very strong persistence. It has a lot of shape to it, but I notice that there's some curvature here, and there's some curvature here, and then, well, there's a little bump. It drops a little bit and it doesn't seem to pick up with the previous trend. So there's more to it than a deterministic function of time that just looks like a line. It's a bit more complicated than that. Still, The time variable would be a reasonable first approximation for predicting data like this. When we talk about forecasting, I don't necessarily need to disentangle why this thing is changing across time. GDP grows across time for a lot of reasons that economists might want to study, and orders that your business is receiving could grow across time for a lot of reasons that your business might be interested in studying, but it might just be that the town you're in is growing, and the growth of the town doesn't need to be explained any further. The primary concern is that your orders are increasing and you need to tool up for a little bit more business. It's the same idea here. We're going from descriptive analytics to predictive analytics, and the goal is no longer to explain why things are happening or which variables are directly related to which variables, but it's more so just to predict the outcome. So the variable y is the whole goal here more than the variable x. Okay, that's a pretty big bifurcation. But also, if I go back and look at orders, what do I have to work with here? In fact, I only have orders and a variable I cooked up that simply counts the order of these orders, which is not a pun that is intended. But the first set of orders, the second, the third month worth of orders, fourth, fifth, and sixth, they're in order. And I have a variable for that. I'm not correlating orders to other variables on the right-hand side that we would typically call x. I'm going to use the time variable to do all of the work here. And as long as this has a nice, stable structure across time, of course we see the seasonality too, as long as there's a stable structure across time, I can use just the time variable as an explanatory variable. Or perhaps I could consider seasonal components, or perhaps I could consider past orders and use those to predict future orders, which we would call autoregressive, in the sense that I'm regressing orders on past values of orders, the same variable. But this is all new ideas that we can do in time series with just one variable. All of this grows from the fact that it has a time dimension and there's a specific order to these observations. Okay, so that's new. We're going to focus first in this deck of slides on models of deterministic trends, where the trend does something very predictable, an easy mechanical function of time like a linear or quadratic or cubic trend. This is good in a short run analysis. We do not recommend these models for predicting the long run. So as far as predicting monthly orders a couple of months into the future, this might be a reasonable way to go. As far as predicting monthly orders in the long run, say 5 years or 10 years into the future, I do not expect this to perform well at all. There are other types of trends, which we might call stochastic trends. This includes that autoregressive model that I just mentioned, just alluded to a little bit, and those will do better when I'm talking about predicting the long-run behavior of a series. And some other sort of ad hoc methods that we have available will do better for predicting long-run behavior of a series. All right, so each of these deterministic trend models is just going to set yt to be some sort of a function of time. That function can be any function of time that you write down, and the time variable can be different things. The simplest possible option would be to say something like yt. Also, notice my index is switching gears here as well. Because this is time series, I'm using t instead of I. So I'll say t is not equal to I. Yay. It's almost the same. The only difference is t comes with a natural order assigned to it. 1, 2, 3, 4, 5. When I talk about cross-sectional data and I just have I doesn't necessarily mean anything in terms of who came first or who is the tallest or anything else. I is sort of a random number that is assigned to each person to keep track of which one is which. That's very different from time. So in a time series, we typically use t down here instead of I, and that's fine. We'll also typically use a capital T as our stand-in for n, the number of observations. So if you see a capital T floating around, that's what's going on. And here when I say t is not equal to I, it's only a little bit different, right? But the capital T and the n are essentially the same thing. It's just the number of observations. In a time series, we use capital T to denote the number of observations because the number of observations also corresponds to the last observation in the series. So if I write y capital T, I'm specifically talking about the very last one, not y1, y2, y3, y4, but y48 in my orders data here. This is the last one here. Right? And from this observation, I would predict the 49th, the 50th, and so on. That number of the observation is only really important here in the time series context. Well, okay, all of that is sort of academic. Let's think about a model. What would I write for yt? Yt might be equal to beta 0 plus beta 1. Normally I would say something like xt, but what could x be in this case? If it's just a linear function of time, xt could be t, the actual time variable. And yes, that's a nice arrow. That's the same t as this one here. It's the same t. So I would never consider putting the index for which observation is which in a cross series on the right-hand side of a model because it's essentially a random number. And I'll go ahead and throw in an error term here and call it epsilon t. That would be easy. Linear trend. Probably the simplest thing that you can come up with. You could make that a little bit more interesting and say something like yt is equal to beta 0 plus beta 1t plus beta 2 t squared. Okay, now I've got the linear piece and a quadratic piece. We'd call this a quadratic trend. Plus epsilon t quadratic. Fair enough. But in every case, yt, when we talk about deterministic trends, yt is going to be some function of time that has a time index baked into it somewhere, and then the error term. And there's a whole philosophy assigned with predicting yt and how this is broken into three pieces. In each of these models, that philosophy works like this. I've got a predictable part of the model, and I've got an unpredictable part of the model. In the second case, I've got a predictable part of the model, and I have an unpredictable part of the model. It's very important in each case to predict the predictable part of the data, predict, as well as possible, because this is going to give you, the predictable part is going to give you your prediction, your point forecast. The unpredictable part, unpredictable, is going to give you your confidence interval. So I will make a point forecast using the predictable part, and then I will add to it, say, 1.96 standard errors. What are the standard errors? They're the unpredictable piece, the standard deviation of that. So it's very important that I can go back to, say, the image of the data with a line fit to it and scrutinize those residuals to ask the question if they're really unpredictable based on the residuals next to them. Again, this is something that wouldn't happen in a cross-section because there's no relationship between the residuals and the residuals next to them. But in a time series, I want a model that will actually follow the shape of this variation because it seems to be predictable. I can see with my eyes that it occurs multiple times. So I want a model that will do that. If I have a model that leaves predictable variation in the residuals, then I've failed to account for that information. My confidence intervals are too large, and my point prediction is probably wrong. So it's sort of a double whammy. Predict this as well as possible. That's where the point prediction comes from. This should be truly unpredictable. That's where the standard error of regression comes from. Okay, big philosophy. And, as it says here, in the simplest case, your trend can be just a simple linear function of time, like regressing orders on month, or it could be something quadratic, or whatever else. And this slide is just to make the point that your time variable could be the actual count index that we've got here, 1, 2, 3, 4, 5, it could be something else like 1950, 1951, 1952, 1953. If I change that out and have a different unit of time, beta 1 will change and beta 0 will probably change, but the fitted values, the predictions for YT based on a new trend component will be the same, right? And in this case, beta 1 increasing implies an increasing trend, upward trend, and beta 1 less than 0 implies a decreasing trend. I said beta 1 increasing, I meant beta 1 positive. All right, this is a fun example, so let's talk through it and point and laugh a little bit. It can be amusing. Figure 5.3 from the old textbook by Frank Diebold. Labor force participation rate for males. It's an old sample. It goes 1950 to a little bit after 2000, and what do you see? It's glaringly obvious that the labor force participation rate for men is dropping during this window of time. Now, it's a pretty clear trend. You could fit a line to this data. Once again, I see little bits of curvature that make me think a real line is going to miss some important variation here. But you could fit a line to this data. The question then would be, would that line predict what is going to happen if I try to step out past the edge of the axis here? So if I try to step out into 2008, 9, 10, 2010, 2011, 2015, 2020, is this trend going to continue? Because if I want to forecast into the future, I need to know how reliable this variation in the past is. Sometimes the data will change abruptly. Well, it seems reliable. It seems like it's a long-running trend, so I suppose it would keep going down. But there are some easy bounds that I can immediately apply to how long this trend can persist. Well, what is the vertical axis? It's the participation rate. It's the proportion in percentage terms, right? So it's the percentage of people in the labor, of people who are of working age and, say, not incarcerated, who are actually in the labor force in the sense of looking for a job or having a job. Okay, well, that can't be less than 0%. I do see it goes from 85 to something like 72. Okay, call it 87 and call it 72. Let's just say it drops 15% over the course of 50 years. In about another 250 years, that trend is going to hit 0. 250 years is an extremely long time. I won't be around to see whether that forecast was accurate or not. But if I try to extrapolate this trend 250 years into the future, it will predict a labor force participation rate for men about 0. And that's sort of unreasonable. It's sort of inherently not valid and not reasonable to extrapolate that far into the future. So right off the bat, you should look at this and think that we're not going to predict much further than, say, the next couple of years. And usually, one step ahead prediction is pretty okay. And predicting further out into the future gets progressively worse and worse until it becomes rapidly nonsensical. Well, all right, men are working less. That sounds very interesting. You might ask why men are working less over time. Maybe progress has happened and there's so much money going around that you don't have to work anymore. One of the other explanations for why men are working less is this one, which is a bit amusing. So, figure 5.1 from the same textbook, labor force participation rate for women. Now, what is happening? It's going from something like 30 as high as 60 over the same time interval. Women are entering the labor force at a rate, at least in the first part of this sample, at a rate faster than 2 to 1 as men are leaving the workforce. So it may well be that women are partially crowding men out of the workforce. And then you could ask, is this really progress? This is suddenly a very interesting story here. But the thing I notice first about this data is something I notice when I look at this quadratic trend. The quadratic trend, unlike the linear trend, which would just do something like this, the quadratic trend would be parabolic. It's a pretty good parabola. I didn't mean to draw it that well. It's going to be parabolic. At some point, it's going to level off, and then it's going to reverse, and it's going to go down, or it'll turn around and go in the opposite direction of whichever direction it was starting. The pro tip we immediately point to is right over here, beta 2. If beta 2 is positive, then I have an upward. I have a convex parabola, concave up, convex down. If beta 2 is negative, then I have the sad face parabola. So, okay. The point is there's going to be this inflection point where it changes direction. Fundamentally, that may or may not make sense for the phenomenon that you're working with to have that property where it increases for a while and then pauses one day and reverses. But here, I do see that happening for some reason. Women are entering the workforce from 1950 to 2000 at a very rapid rate. Something changed in the late 90s going into the 2000s. It leveled off and it started to decline. So I don't know what that is. I don't know why that is. I'm deeply perplexed by it because it's a strange thing to observe. But we do have models that can follow that sort of behavior if we choose to do so. You might look over here and say, well, maybe a linear model is okay in this part of the data, and maybe I need something like a quadratic model in this part of the data, or you might ask if you would use a linear model for the full sample. Of course, a linear model for the full sample is going to continue increasing to the right as I roll the model forward and try to predict the future, but I observe that the data has turned around and gone in the opposite direction, which means a linear model is going to get very, very bad, very, very fast at trying to predict this data. All right. So, how would you potentially scrutinize what's happening? Think about the residuals in the model. The residuals are very important, as I mentioned, because the standard deviation of the residuals is what you're going to use to produce a confidence interval. If you try to predict what's going to happen and then give an upper bound and a lower bound, we're going to talk about the variation in y that is unexplained. The part of y that is unexplained is the residual, the error term. So the residual is always equal to the difference between what actually happened and what you predicted. If what actually happened was a little bit more than what you predicted, then your error term was positive, and if it's vice versa, then your error term is negative. So it's just yt minus whatever sort of stochastic trend model you estimated. It's very important, as this bullet says, very important that you don't see clear trends in the deviations, or you don't see lingering, say, autocorrelation, where the error terms might be used to predict each other. I'll show you an example here in just a second. This is from software called eViews, which is very similar to most statistical software, but eViews, which does regressions and everything else, is a little bit made for time series and forecasting. It's sort of specialized in that way. And it has this cute plot, actual fitted residual plot. Now, we're going to look at some actual and fitted plots in Excel, because Excel with the regression utility will happily plot the line over a scatter plot of the data. And you can do that even when you have multiple right-hand side variables. It can also plot residuals over the right-hand side variable in the data, which in this case is something like time. But here, eViews has done it all in one plot. So I've got the original data, labor force participation rate for men. I've got a line superimposed on the original data. And then down here, I have the residuals, with standard error bands. How about that? And I'm very sad immediately because I see that all of these residuals are positive, well, except for that little one down there. Lots of positive residuals, lots of negative residuals, lots of positive residuals again. There's a lot of correlation in these residuals with their neighbors. If I see a positive residual, I could guess that the next residual is going to be positive, and I would be right very, very, very often if this is my set of residuals. So when the line is too low, when my model is too low, the data are too high, the data stay too high for a while. If I'm giving this forecast and the data look like this and they keep looking too high, I should move my forecast up, right? I see that this line is consistently too low. It's not producing good forecasts in this area. And same thing here. The line is consistently too high. It's not producing good forecasts for this part of the data, and so on. At the end of the sample, if I roll it forward one day, I see that the last several observations have been about 1 standard error of regression above average. I've got all of these positive residuals. When I make the next prediction, I would predict a positive residual as well. That's a problem because the residuals are supposed to be 0 on average. I'm supposed to predict the residual to be 0. If I can predict the residual any better than that, then my model isn't incorporating the obvious information in the data. Okay, well, here's what happens when you look at the labor force participation rate for women. Same thing. Over here in the sample, I have smaller residuals, so that's good, but they are in fact positive, a little bit correlated, then they go negative, then they go positive for a while, and then they really go off the charts when this model continues marching upward as we move further to the right, while the data pause, level off, and then turn around to start to come down. So on the right end of this window of time, the model is very, very, very badly fitting the data. This is also sort of a cautionary tale about how much data you should use in a trend model. This is a long window of time. If I fit a line just, let me go back to the clean picture. If I fit a line just to the last little bit of data, I'll probably get a better forecast a couple of years into the future than if I try to fit a line to this full 50 years of data. That sounds like a paradox. That sounds like a conundrum because essentially I'm saying I'm going to get a better forecast if I use less data than if I use more data. But in a case like this, where I think that the model is probably a poor fit to the data, it may well be the case that I get a better forecast when I use less data and only fit these last however many years. Which could, in monthly data, is still going to be say 10 years monthly data. That's still 120 observations, is not exactly a small number. So, okay, things to think about. Well, where can we go next? Let's try a quadratic trend. No reason not to. Let's make it a little bit crazy. Put t here and then put t squared there, and we'll see if the quadratic trend does a little bit better. Cute caveat here, right? Note that a linear trend is a special case of a quadratic trend with beta 2 equals to 0. So this model, the worst this model can do is give you beta 2 equals 0 and give you the linear trend back. But if beta 2 greater than or less than 0, if beta 2 for any value other than 0 produces a smaller sum of squared residuals, then that's the value that you're going to get, and you're going to get a model that is better, strictly better, than the model that only has a linear trend in terms of what? In terms of the size of the squared residuals and in terms of regular old r squared. So adding another variable to the model always increases r squared. That's what's happening here. Well, here's some particularly troublesome data. Look how flat it is at this point in time. Now, I might think about trying to come up with an exponential trend, something that grows very, very rapidly. That's doable, but it comes with its own basket of maladies. So I see that it's very, very flat over here, and then it grows really rapidly, but then it levels off a little bit again. So I'm not sure what to do. I think a linear trend is probably going to be too weak, and I try something like a quadratic trend. Here, once again, negative errors all the way through here, positive errors all the way through here. Then the residuals turn negative and then turn positive again. And by the end of the sample, I don't have a lot of faith that this model is predicting the residuals are positive at the end of the sample. So I don't have a lot of faith that this model is going to give me an unbiased prediction of what will happen in 2006 or 2007 or so on. So sometimes statistics or applied statistics is just a long, long list of things not to do. Let me show you all of the bad examples for why this doesn't work, and then you'll be able to identify, if you have a similar example, whether it's working or not, because it will fail in the same ways. The big warning here is about higher order polynomials. You might say, well, the linear trend and the quadratic trend are not good enough, so let's do something stylish like yt is equal to beta 0 plus beta 1t plus beta 2 t squared plus beta 3 t cubed. Aha! Now I've got a cubic function in time plus an error term. And instead of a line or a parabola, the cubic function will do something like this. Interesting. Now, a cubic function is going to have 2 inflection points. That's the first thing to say about this. Do you really believe you're dealing with a type of data set that can do that? The next big problem is, fundamentally, if we talk about polynomials and how we factor polynomials and how many roots a polynomial can have, and you do all of the algebra theory, you define a line using only 2 points. You can fully define a parabola using only 3 points. You can fully, exactly, and perfectly define a cubic model using only 4 points, and so on. So if I have, say, 48 observations in my data set over here about orders, well, 48 observations can be exactly fit by a polynomial of order 47. So if I go all the way out to not linear, quadratic, or cubic, but I keep adding terms until I get all the way to beta 47 t to the power of 47. Now that's a ridiculously large model, including 47 variables on the right-hand side, but my r squared will be equal to 1. That's actually not good. R squared equal to 1 means that the model will not only explain the predictable part of, say, the data, imagining that this is a true model, it will also explain away the error terms. So the error terms are truly supposed to be unpredictable. That's where the confidence intervals for my prediction come from. If I have a model that fully explains those, my confidence intervals, because the standard error of regression would be 0, my confidence intervals are all perfectly narrow. They have width of 0. Everything is just point forecasts. Well, obviously that's unreasonable because there is variation in the data that's unpredictable. I would have this false sense of precision, and this giant model that goes up to something like beta 47 is going to go right off the charts as soon as I step a couple of observations into the future and try to predict with it. These higher order polynomial models are very, very, very much frowned upon because of this overfitting. Okay, so can we do it? Yes. Higher order polynomials can fit more complicated trends. They can do crazy things. We very strongly, in any kind of forecasting context, scrutinize those models, and we are wary of going past maybe cubic. There is this caveat here, all right? So include low order terms to maintain smoothness / flexibility of trends. If you're going to do something like a quadratic trend, include this, right? Always include the first one. Don't just go straight for t squared. Include regular t and then add t squared. If you're doing cubic, include t squared, include t. There's no reason to restrict those. You're putting it's not obvious what leaving t out of a cubic trend is going to do, but it is going to put some sort of a strange restriction on how that polynomial can behave. And again, we don't want to do that because we're not really sure what that restriction looks like in most cases. Okay, so deterministic trends as an approximation, quadratic trends are U-shaped. Think about this change point property. Are you working with data that can have this turning around happening? This inflection point? Many time series do not have that property. In general, all the data may lie on one side or the other side of the U-curve. Do you really want a model that can turn around and go in the other direction as you forecast into the future? In some cases, that's going to give you very strange behavior, right? And it extrapolates to cubic and quartic and quintic and whatever comes after the polynomial of degree 5. Here's an example. Real GDP in Japan, some old data, again 1960 to 2010, and I'll be honest, even though it's got a little bit of a couple of bumps going on here, this looks like something that a parabola would fit really well. But if I did what would that parabola do? It would level off about here, and then it would start to come back down as I roll the model further forward into the future. I don't believe that GDP in Japan is going to turn around and start going down. And I certainly, what is this, 1960 to 2010? So by 50 or 100 years into the future, that quadratic polynomial will go down and predict Japan's GDP inevitably would go to zero, and then actually would become negative after that, which is sort of ridiculous. So it's just not reasonable to try to use a model like that and forecast too far into the future. I certainly hope, for the sake of Japan, that their GDP doesn't start to decrease and maybe it starts to grow again would be preferable. So these higher order polynomials are very, very dubious. And in the limit, as t goes to infinity, all of these deterministic trends are either going to go to positive infinity or negative infinity. And it'll depend on the sign of the coefficients as far as which way they're going, but you can think about that too and try to decide whether you think it's reasonable to use one of those models for anything more than just predicting a few steps into the future. Okay. So the good news is, as far as estimating each of these things, the set of parameters that plug into a model, if you've got a trend defined by some sort of a model, we're still just doing ordinary least squares, and it's easy enough when I have just something like yt minus beta 0 minus beta 1, whatever my time variable is. That would be my error term. Square those, add them up, and find the beta 0 and the beta 1 that minimize the sum of squared errors, and it's just regular old ordinary least squares. If I have the quadratic version of that, I do the exact same thing. Yt minus beta 0 minus beta 1, my time variable, minus beta 2, my time variable squared. Square all of those error terms, add them up, and minimize it in order to find beta 0, beta 1, and beta 2 for ordinary least squares. This model is still linear in terms of parameters, so it's still linear algebra. The solution doesn't really change. These are two separate regressors, so if I pop back to the data set, I will have to generate a variable for time squared. I'm going to have to do that over here, make a new variable, month squared, and include that in a regression. But that's easy enough. And then the last piece of the puzzle is there's not a perfect collinearity problem here. Although time and time squared are going to be strongly correlated, I don't have to worry about perfect collinearity because time squared, x squared, is not a linear function of x. Time squared is not a linear function of time. So it's imperfect collinearity, but this multicollinearity does tend to result in these two variables being less significant than they would have been if I had included only one of them in the model. Something to worry about in a setting where we were more concerned about scrutinizing time or time squared in terms of their t-statistics. But for forecasting, that's not a problem at all. So I'll end this video here, and in the next video, we'll jump over to the data and we'll estimate some of these, and then talk a little bit more about model selection.